Hello, students, and welcome back to eCoreAcademy. My name is Anita Raj, and I'm one of the teachers and co-founders here, along with my younger brother, AJ Raj. As you can see today, we have a new Algebra 2 lesson. I'm sorry it was a long time in the making, but trust me, it's going to be worth it because we're going to be continuing our series of lessons on rational functions and their graphs as requested by some students. And today our focus is going to be wholes and asymptotes. Specifically, we're going to be looking at different functions and we're going to be seeing how can we determine if it has a whole or an asymptote, and then based off of that, how do we graphically represent those? So we're going to first be understanding the properties of wholes, vertical asymptotes, and horizontal asymptotes. We're going to be understanding what they are and when they occur, and then we're going to be going over steps on how to graphically represent them because they are vital to the graphs of these rational functions, meaning you do have to represent them when you are graphing on homework or an assessment or whatever. You need to show that there exists some kind of discontinuity, whether it be a whole or an asymptote in the case of rational functions. So that's what we're going to cover today. Before I get into the lesson, I do want to do two things. First, I want to show you just kind of acknowledge the image I have up here. It says "Can't touch this," and I think there's a song that was in the United States called "You Can't Touch This" by MC Hammer a while ago, and it was super popular. You can just go on YouTube, you can open up a new page of YouTube and not Google it, but search it up, and you can listen to it. But it was a pretty famous song. I remember listening to it when I was in elementary school. And when we say you can't touch this, if you look at the graph, it's of a rational function, and you can see that there is a vertical asymptote at what looks as if it is x equals 1, and there's a horizontal asymptote at y equals 1. You can see it on the graph, and you can see the curves of the graph are approaching those asymptotes, but they're never going to be equal to whatever value the asymptote is. So, for example, the value of x equals 1 is undefined for this rational function, and then no x value is going to have an output or a corresponding y value of 1. So they're going to approach those values, but they're never going to actually touch the asymptotes. The curves are just going to approach them infinitely. And remember, we talked about discontinuities. In this case, they're just going to approach them without bound. So I just wanted to talk about that, and you can even see here the limit. It says the limit as x approaches infinity. So it's just going to increase or decrease without bound in regards to this rational function. So I thought that was pretty neat, and I thought that was kind of funny, a way to think about it, just to help you remember what are asymptotes. The curve is not going to touch the asymptote. That's what an asymptote is. It's not going to touch that value. And before we get started with the lesson, I'd really appreciate it if you all could subscribe, hit the post notification bell, drop a comment down below, and share using our socials. This is a super valuable lesson, and I'd really appreciate it if you could spread the word about it to those who could use it. All right, so let's get to the first slide, and we're going to first talk about the properties of wholes. These are the smallest discontinuity if you want to think about it size-wise. These asymptotes are like lines that go on for infinity. So let's start off small. Let's start off with wholes. So points of discontinuity often result in vertical asymptotes. As we've seen, we're all probably very familiar with vertical asymptotes because almost every rational function will have a vertical asymptote, that hatched vertical line, and the equation of a vertical asymptote is x equals a, and a is it's a number where the discontinuity occurs, and we'll talk about how we determine where a vertical asymptote occurs for a rational function later on. But my point is that usually when we talk about points of discontinuity for rational functions, we're talking about vertical asymptotes. But however, sometimes there's going to be a hole that's going to be created by the rational function. And when we think about when does a hole occur, well, a hole occurs when a value is a 0 of both the numerator and the denominator. As we talked about before, usually the numerator and denominator. The numerator we call p of x, and the denominator we call q of x. They're both polynomials, and what you can do is you can actually factor these polynomials. From the examples we've been looking at, they've usually been quadratics and then a linear term. One is either the numerator, one's either the denominator, and then what happens is we'll factor them, and then we'll see do they have common factors. Remember, when we factor a polynomial and we solve, so we factor and then we set it equal to 0. That's called a solution an x-intercept, whatever you want to call it. So in this case, you're going to call it a 0. So those common factors are considered zeros. When we set them equal to 0, then we solve for x. So when we factor the numerator and denominator, we find that they have common factors that actually cancel out, because remember, we're dividing these polynomials. Then we're going to have something called a whole, and that's when a whole is created. So we're going to look at how do we identify when a graph contains a whole, and what are we going to do about it to represent it graphically. So let's think about the graph of the function x squared minus 3x minus 4, that whole quadratic trinomial divided by the linear binomial x minus 4. Okay, let's just think about the graph of this. So our first step that we want to do when we approach graphing any rational function, we want to start by identifying what the zeros are. So the zeros can be determined by looking at the denominator and setting it equal to 0. So in this case, our denominator is pretty straightforward. It's a linear binomial x minus 4. We're just going to set x minus 4 equal to 0, add 4 to both sides, and find that x is equal to 4. That's a 0. Our second step is we're going to reduce the function. So what does that mean? Reduce the function pretty much just means simplify. So if one of our numerator or denominator is a polynomial, we're going to try to factor it and see does a term in the numerator cancel out with a term in the denominator? Are there common factors, etc.? So we're going to try to simplify the function we've been given. That's what reduce means. So f of x equals, well, we can actually factor x squared minus 3x minus 4 to x minus 4 times x plus 1. That's just the guess and check method that we learned with quadratics. And then we're going to divide that by the denominator we were previously talking about, which was x minus 4. And in this case, you can see that the numerator and denominator have a common factor of x minus 4. So what we can do is we can pretty much cross those out. So if I actually draw it here, what I usually do, and I'll show you on the next slide, I'll actually just cross these out like that to show that they've canceled out with each other because division is happening here. And all that we're left with is f of x equals x plus 1. We're only left with this factor right here of the numerator. So that's how we simplify our function. So we're going to rewrite the function as f of x equals x plus 1, but that does not mean we're ignoring that there was a common factor of x minus 4. You'll see how that plays into our steps with graphing. Our third step is we're going to plug in the 0 or zeros, in this case there's just one 0, you found into the reduced function to find the whole or wholes in the graph. So in this case we said the 0 was x equals 4, and like I said, we're not going to ignore that. What we're going to do is we're going to take that 0, x equals 4, and plug it back into the reduced or simplified function we found. The simplified function we found was f of x equals x plus 1. We're going to take 4 and we're going to plug it in to f of x. So we're going to try to find f of 4. Remember, when we find f of 4, f of any x value is equal to the corresponding y coordinate. So in this case, we're trying to find the y coordinate that goes along with the x coordinate, x equals 4. Because if we find that coordinate, we know where the whole occurs in this graph. So we're going to find f of 4. F of 4 is equal to, well, x plus 1, and we're going to substitute 4 in for x. So 4 plus 1 is equal to 5. 5 is going to be our y coordinate. So we're going to have the point 4, 5 as the coordinate where the whole occurs in this graph. And then lastly, all you have to do is plot the points to complete the graph. What we're going to do is I'm going to show you how to do this on the next slide because we obviously don't have space here. So we're going to plot these points, connect them, and then represent this rational function. All right, let's do this on the next slide. So we're going to be graphing wholes here, and here's we're literally just going to use the same exact equation we used on the last slide. We're actually going to be graphically representing this. Here's your solution pre-written. I know it's a bit small if you're viewing it on a phone, but I'm just going to go through it again, and hopefully I can write it a bit bigger. Obviously, when you do these, you don't need to, it really depends on your teacher, because my teacher did require us to show all work, and that's why I go very in depth with the work I show. Also, so because I'm teaching and I have to show you all the work so you understand it. And I'm not sure how much your teacher requires, but I recommend writing everything out just so you know where your thought process is going. All right, that being said, I'm going to work through this problem with you with a blank graph. So first, I'm just going to rewrite the function we were working with, the rational function. F of x was equal to x squared minus 3x minus 4, and I'm just taking this from the last slide, divided by x minus 4, our linear binomial. The first thing we want to do, the first step we want to do is we're going to find our 0, so we're going to set the denominator equal to 0. I'm repeating what we did on the last slide just as a little refresher. So we're setting x minus 4 equal to 0. If we add 4 to both sides, we get x is equal to 4. That's where our 0 occurs. Now we want to reduce the function. So I'm going to rewrite the function x squared minus 3x minus 4 over x minus 4. Luckily, we're working with quadratics, which we're pretty familiar with, so we're going to use the guess and check method to factor the top. Well, let me look at 4. Factors of 4 include 1 and 4, and if we think about it, we need a -3. So if I have a -4 and a +1, they both add up to -3, and a -4 times a +1 is equal to a -4. So my factors are going to be x plus 1 times x minus 4 divided by, don't forget our denominator, which was x minus 4. And then like I showed you on the previous slide, we have common factors between the numerator and denominator, which are going to cancel out. And we're going to be left with x plus 1. Well, what are we going to do with this x plus 1? Well, this is our reduced function, so we're going to rewrite f of x as equal to x plus 1. But we're not going to forget that x minus 4 we had. What we're going to do with that is we found our 0 to be 4. So this is going to be where the whole occurs. So what we're going to do is we're going to plug 4 into f of x to find the corresponding y coordinate where the whole occurs. So f of 4 is equal to, remember our reduced function was x plus 1, so we're going to substitute 4 in for x. We're going to get 4 plus 1, and then we are going to get 5. And what does that mean? Well, that means that the whole occurs at the point 4, 5. So now what are we going to do? How are we going to graph this? Well, we know a whole occurs at 4, 5, but we don't know any other points that belong on this function. And we have to figure out some more points. And what do? Well, we bring in our XY table. It's always trusty. We always use our XY table. And then what we're going to do is we're going to put our point 4, 5 smack in the middle, because we want that to be like the central point, the focus of our graph. It just makes it a lot easier to make sure. The reason why we put these discontinuities in the middle of our XY table is because we want to find points around it so that when we graph, we make sure that we are including our discontinuity. If we put it at the top or the bottom of our XY table and find values that come after or before it, then it might be smushed all the way to the side of a graph or something like that. So we want it to be like the central focus point of the graph, so we're going to put it in the middle. And then we're going to find points that are, we're going to pick x values that are less than it. So we're going to pick 2 and 3. We're going to pick x values that are bigger than it, 5 and 6. There's no rhyme or reason. You could have gone like 2 minus, you could have picked 2 and -1, or you could have picked 6 and 8, whatever you want to do. Just for our case, I just picked these numbers. And you're going to take these x values, and then you're going to plug them into the reduced function. So we're going to plug 2 in for x. 2 plus 1 is equal to 3. Plug 3 in for x. 3 plus 1 is 4. Plug 5 in for x. 5 plus 1 is 6. Plug 6 in for x. 6 plus 1 is 7. All right, so now we have our XY table, and now we're going to start plotting the points. The first point I would plot is your discontinuity, so you don't forget about it. A common mistake people might make is that they actually just plot a normal point. Like, for example, we have the point 2, 3. So if I find that on the graph, it's right here. And then if I just draw the point 2, 3 right there, okay, we're done. So you might do the same thing with the whole. You might go to the point 4, 5, and you might just draw a closed circle. But it's a whole, so it's supposed to be an open circle. So make sure, that's why I write in my XY table, I point at it and I say whole. It's like a glaring signal, like this is the whole. Make sure you don't plot a closed circle. Make sure you're plotting an open circle, because you're trying to show this isn't a regular linear equation. Because if you look at f of x equals x plus 1, it looks like y equals mx plus b, like a regular linear equation, which is a line. But this isn't a regular linear equation because this has a discontinuity at x equals 4. So make sure you're graphically representing that discontinuity. So let's just go about pointing the rest of the points. There's a point 3, 4, so 3, 4. The point 5, 6 here, and then the point 6, 7 here. You can obviously just keep plotting it because you can see that this is like almost like a linear equation once you get past the discontinuity. But for our case, I'm just going to sketch the rest of it. So this is going to continue like that, and then this is going to continue. Sorry if it's like a sketch, so I'm just going to. All right, so I did my best. So that's how your graph is going to look, and that's how you would graphically represent this function with a hole in it. All right, so let's move on to the next slide. And now we're going to be talking about properties of vertical asymptotes. Like we talked about before, I feel like we've been focusing a lot on vertical asymptotes. It's been like the main focus of most of our lessons with discontinuities. So let's talk a bit more about it. I just have a few things I want to go over, just 3 main things that I want to bring up. And that's really it for vertical asymptotes, because by now, I think all of you are masters at vertical asymptotes. The first thing I want to bring up is the rational function f of x equals p of x over q of x has a point of discontinuity for each real 0 of q of x. So what does that mean? Well, obviously, our rational function comes in the form f of x over p equals p of x over q of x. P of x is your numerator, Q of x is your denominator, and both of them are going to be polynomials. They're going to be maybe constant. Sometimes you're dealing with a constant term. You'll deal with a linear term, a quadratic term, cubic, etc., etc. And you don't know how many terms you might have. You might have a binomial, a trinomial, a monomial, or a polynomial. So P of x and Q of x, you're pretty much dividing them. And you're going to find a point. So your rational function is going to have a point of discontinuity for each real zero of Q of x. What does that mean? Like we said, Q of x is a polynomial, meaning you can usually factor it. And when you factor it, and then you set your factors equal to 0, and you determine what value x has to be equal so that polynomial is equal to 0, you're finding your real zeros, your solutions, your x-intercepts, your roots, like we talked about before. Each of those, sometimes you might have one, like we saw in the last example with x minus 4 equals 0. We found that x equals 4 is our point of discontinuity. Sometimes if Q of x is a quadratic that you can factor, you might have 2 zeros. If it's a cubic that you can factor, it might have 3 zeros. You never know. So it really just comes down to factoring and solving for Q of x. By setting it equal to 0. So each value that x is equal to, every zero that you have for Q of x is a point of discontinuity. So every single one, because Q of x is our denominator, and if we set Q of x equal to, if we set x equal to a value that makes Q of x equal to 0, then what's going to happen is we're going to have P of x divided by Q of x becomes 0, so P of x divided by 0, and any number divided by 0 is undefined. We can divide, if P of x is equal to 0 and we divide it by Q of x, then that's okay. You can divide 0 by a number, but you cannot divide a number, or a polynomial in this case, by 0. So that's where your points of discontinuity get created, your holes, your vertical asymptotes. That's where you get your points of discontinuity. If P of x and Q of x have no common real zeros, so that means that if we factor P of x and Q of x, like we did in the last problem, and they don't have any common factors, meaning, I'll show you an example, like if we have something like f of x is equal to P of x over Q of x. Let's say P of x was equal to, I don't know, I'm just going to say x plus 2 times x plus 3. If you multiply that out, you're going to get a quadratic trinomial, but let's pretend we already factored it. And then let's say Q of x is equal to x plus 1 times, x plus 1 times x plus 4. Let's say we already factored Q of x. As you can see, there's no common factors here. So what's going to happen is no common real zeros, pretty much no common factors. In the last problem, we had a common factor of x minus 4. This problem, we don't have any common factors. So what's going to happen is we're going to just look at, then the graph of f of x has a vertical asymptote at each real zero of Q of x. So we're going to disregard P of x for now. We're just going to focus on Q of x. And here we have two real zeros. We have a 0 at x plus 1 equals 0. So we have a 0 at x equals negative 1. And we have a 0 at x plus 4 equals 0. So we have a 0 at x equals negative 4. So we have zeros there, but because there were no common factors, those zeros are discontinuities, and they're specifically going to be vertical asymptotes. On the flip side, if P of x and Q of x do have a common real zero, which is, we're just going to call it point A, so x equals A, then there's going to be a hole in the graph at the point x equals A. And I'll give you another example that kind of highlights that. So if we had f of x is equal to P of x divided by Q of x, and let's say P of x was equal to, I don't know, x plus 2, let's say we already factored it, x plus 2 times x plus 1, and divided by x plus 1, well, there's a common factor here, which is x plus 1. So that's going to mean that if we set x plus 1 equal to 0 to find the 0 is going to be x is equal to negative 1, and there's not going to be a vertical asymptote here. There's actually going to be a hole here because there's a common factor. We can find the corresponding y coordinate by plugging negative 1 in for x, and if we do f of negative 1, we end up getting, if we see the reduced function, now all we're left with is x plus 2. So we plug negative 1 in for x, we get negative 1 plus 2. Negative 1 plus 2 is equal to 1. So our hole is going to occur at the point negative 1, 1. So those are the kinds of discontinuities we're going to be dealing with and we've dealt with so far. But what are we going to be diving into that's new in this lesson? And that's going to be properties of horizontal asymptotes. So vertical asymptotes go up and down like this. I don't really know how else to describe them. Think of like holding a ruler up and then it's like up, straight up and down. Horizontal asymptote is going to be like the horizon, like the sunset. It's going to be going across like that. So that's those are horizontal asymptotes. And let's look at some properties now. So horizontal asymptotes are horizontal lines the graph approaches as x gets infinitely large or small. So what's going to happen is it's going to focus a lot on like the denominator, and there are different rules for finding horizontal asymptotes that we're going to go over. But if you think of a vertical asymptote, if you think of a curve of a function, it approaches the vertical asymptote, but it's never going to touch it. So it's going to get very, very close. Meaning, think about limits, like we talked about in the last video. It's going to get very, very close to that vertical asymptote, but it's never going to touch it. Same thing with horizontal asymptotes, except they're not up and down like this; they're across. A curve of a function is going to approach that line as x gets infinitely larger or small, but it's never going to touch that line. And when we say x gets infinitely larger or small, I'll talk about what that means in this example. I think this is a good example. So think about the example. For example, what happens to the function f of x equals 1 divided by x? So the numerator p of x is 1, it's a constant, and then q of x, the denominator, is x, which is a linear term. What happens to this function as x gets infinitely larger? Let's think about it logically. So if x is equal to, let's say, 2, then f of x equals 1/2. Okay. What if we increase x to 4? F of x equals 1/4, and that fraction 1/4 is less than the fraction 1/2. Let's say we increase x to 1,000. F of x is equal to 1 over 1,000. That's even smaller than 1/4, which is even smaller than 1/2. So what happens to the function? What happens to the value of the function, which is the y-coordinate, or the output, as x gets larger? Well, the value of the function is going to get smaller. And what does that mean? Well, f of x is infinitely smaller. But think about it this way. X cannot be equal to 0. No matter what, x cannot be equal to 0, because if x is equal to 0, we have a discontinuity there. We have a vertical asymptote there. However, what happens is, as you increase x, you're going to get larger and larger. The fraction's going to get, x is going to get larger and larger, but the fraction is going to get smaller and smaller, meaning you're going to go down to 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000. And that fraction is going to get closer and closer to a y value of 0, because the smaller fraction you're going, the closer you're getting to 0, but you're never going to get to x, you're never going to get to 0, because x cannot be equal to 0, because there's a discontinuity there. You can't have 1 over 0. So f of x is just going to get infinitely smaller, but it's never going to be y equals 0. Therefore, y equals 0 is a horizontal asymptote of f of x equals 1 over x. It's a lot easier to explain this when we graph it, which I will graph it at the end of this lesson, but because it's getting infinitely smaller, like 1 over 1,000,000, 1 over 1,000,000,000, y is approaching, the value of the function approaching 0, but it's never going to be 0. So the curve is approaching 0, but it's never going to be 0. So y equals 0 is a horizontal asymptote of this function f of x equals 1 over x. And the graph of a rational function has at most one horizontal asymptote. So for rational functions specifically, you're just going to have one. So you don't have to worry about, like we had to do with holes and vertical asymptotes, finding multiple. If there is a horizontal asymptote for rational function, there's only going to be one. There are cases when you're getting a pre-calc. For example, the graph of the sine wave, the sinusoidal wave, the graph of cosine, the graph of secant and cosecant, which are like the reciprocals of sine and cosine. Those all actually have they have two horizontal asymptotes, but those are not rational functions. So you don't need to worry about them for now. For rational functions, we'll have at most one horizontal asymptote. So let's talk about how do we find horizontal asymptotes. There are three main scenarios I'm putting up 4 fingers. There are 3 main scenarios you're going to run into when you're trying to find horizontal asymptotes. But the main thing I want you to keep in mind, the main kind of tactic that you're going to apply is you're going to determine what the degree of the numerator and the degree of the denominator are. Remember, hopefully you remember degrees from our polynomial lessons. So degree is going to be when you have a polynomial. Doesn't matter how many terms are in it or what. Doesn't matter how many terms are in it. You're going to order it from the term with the highest degree to the term with the lowest degree. For example, if we have the polynomial x cubed plus 2x squared plus x minus 1. The x cubed, which is the first term, your leading term, has the highest degree because it's raised to the highest power out of all of these four terms. That's going to be your leading term. And that term's exponent determines the degree of the polynomial. So the degree of the polynomial in this case I just gave you, the first term was x cubed. So the degree is going to be a third degree polynomial. So it's going to be like a cubic. It's going to be a cubic. So you're going to determine what that degree is for the numerator p of x and the denominator q of x. And then after determining that, I'll tell you where to go about. So if you determine the degrees of the numerator and denominator and you find that the degree of the denominator is greater than the degree of the numerator, then you're automatically going to know there's a horizontal asymptote at y equals 0. Well, why does this make sense? Because what happens is if you plug in an x value, if you increase x and you plug in x values, the denominator is going to be larger than the numerator. That means that if you divide a small number by a larger number, you're going to get smaller and smaller and smaller. That fraction is going to get smaller and smaller and smaller, like we said in the previous slide, and it's going to get closer and closer to 0 the smaller the fraction is. So, for example, if we have y equals 1 over x, which was the problem we looked at the last slide, the degree of the numerator, which is 1, is equal to 0 because it's just a constant. The degree of the denominator, which is x, it's a linear term, so it's 1. In this case, 1 is greater than 0, so the denominator has a greater term than the numerator. And we're automatically going to know that there's a horizontal asymptote at y equals 0. If you look at the next example, y equals x divided by x cubed. The degree of the numerator is the degree of the numerator is 1 because x is a linear term. It's raised to x to the power of 1. And if you look at the denominator, it's x cubed. The degree of the denominator is 3 because the exponent x is raised to, in this case, is 3. And again, the degree of the denominator is greater than the degree of the numerator. 3 is greater than 1. So we're automatically going to know for this problem as well, the horizontal asymptote is going to be y equals 0. In our next scenario, if we analyze the degrees of the numerator and denominator and find that they're both equal to each other, then we're going to know that there's a horizontal asymptote at y equals a divided by b. How do we determine what a divided by b is? Well, a and b are the coefficients of the highest term in the numerator and the denominator. So a is going to be the coefficient of the highest term in the numerator, and then b is going to be the coefficient of the highest term in the denominator. So in this example, y equals x squared plus 2x plus 1, which is a quadratic trinomial, divided by 3x squared plus 2, which is also a quadratic, but it's a binomial. If we look at, we can see that if you look at the leading terms, if you look at the degrees of both, well, the degree of the numerator is 2 because it's x squared. The first term is x squared. But the degree of the denominator is also 2 because the degree of that quadratic is also 2. They're both quadratic, so they both have the same degree. So what you're going to do is you're going to determine what a is. So you're going to take the leading term of the numerator, which was x squared, and you're going to determine what's the coefficient of the numerator. Coefficient of x squared is 1. You can think of it like an invisible 1 is there. I think we all know this basic rule by now. The coefficient of x squared is 1. Then you're going to look at the leading term of the denominator, which is 3x squared, and you're going to determine what is the coefficient of 3x squared, and that is 3. Then what you're going to do is you're going to divide a by b. So a is 1, b is 3. So then your horizontal asymptote, which is abbreviated as HA, which you can abbreviate it as because writing horizontal asymptote out is a lot. So your horizontal asymptote is going to be equal to y equals 1 divided by 3. And the last scenario is pretty simple. If the degree of the numerator is greater, then the graph has no horizontal asymptote. And this makes sense because in our first example with the whole, you saw that the degree of the numerator was a quadratic, and then the denominator was a linear term. And we were able to find a common factor and simplify it. And what we were left with was a line, and a line has albeit one discontinuity at one point, but a line doesn't have a horizontal asymptote. So what happens is there's really no problems when your numerator is bigger than your denominator because you're dividing a large number by a small number. So you shouldn't have a problem where when you reduce the function, you're left with a fraction. And if you're left with some kind of fraction, what's going to happen is if you plug x in, then the fraction, the y value is just going to get increasingly smaller. In this case, we have no horizontal asymptote because the numerator is already going to be greater than the denominator in terms of degree. All right, so now let's just practice some horizontal asymptotes. So we're going to find the horizontal asymptotes of 4 different functions, but we're not going to do it. We're not going to graph at all. So our first example is y equals 2x divided by x minus 3. We're going to determine the degrees of the numerator and denominator. The degree of the numerator, 2x, is equal to 1. The degree of the leading term in the denominator, which is x, is equal to 1. And if you see 1 is equal to 1, so the numerator and denominator have the same degree. So then we're going to go into our coefficient, and we're going to determine y equals a divided by b. So the leading coefficient of 2x is equal to 2, leading coefficient of x is 1, and if we divide a by b, we're dividing 2 by 1, and we're going to get 2. So our horizontal asymptote is going to be y equals 2. In our next example, we have y equals x minus 2 divided by the quadratic trinomial x squared minus 2x minus 3. The degree of the numerator is, which we're going to look at x for, so the degree of x is equal to 1. It's just a linear term. And then the degree of the denominator, we're going to look at x squared, which is the leading term, and the degree of the x squared is 2. And if we see 1 is less than 2, meaning a is less than b, meaning the numerator has a lower degree than the denominator. And when the denominator has a greater term, we remember that horizontal asymptote is going to be y equals 0, because if the numerator is bigger, as we plug in greater x values, the fractions get smaller and smaller and going to approach y equals 0, but it's never going to actually be equal to y equals 0. Then if we have the function y equals x squared divided by 2x minus 5, what we're going to do is we're going to determine the degrees of the numerator and denominator. X squared is the only term in the numerator, and the degree of x squared is 2 because it's a quadratic. The leading term of the denominator is 2x, and it is a linear term, so it has a degree of 1. So in this case, 2 is greater than 1, meaning a is greater than b, meaning the numerator has a higher degree than the denominator. And when that happens, we have no horizontal asymptote at all, because we're dividing a large number by a small number, and we're not going to have any infinitely getting smaller fraction kind of scenario. And in our last example, y equals 2 divided by x minus 1, that's going to be our rational function. And then we're going to have a plus 3. So I don't think I talked about translations. I think that came in a different lesson. But you can actually translate rational functions. And in this case, when we add that plus 3, we're actually, just like when you have y equals mx plus b, that b is your y-intercept, and it's kind of moving your y equals x function up and down, that line up and down. In this case, the 3 is going to move our rational function up 3. So we're going to pretty much disregard any of the degree or coefficient rules that we've been following because we have that plus 3 added to the end of it. So it's pretty much written like, I'm going to write it up here. So that would be written as y equals 2 over x minus 1. And then we add the plus 3 over here. So this plus 3 kind of changes things. We're going to translate it 3 units up, and we're going to disregard any degree or coefficient comparisons. We're immediately going to know the horizontal asymptote has been shifted 3 units up. So it's going to be y equals 3. Now, I just want to say before we actually get into one last graphing problem, if you want to represent a horizontal asymptote graphically, which you need to if the graph has a horizontal asymptote, you're pretty much going to do what you do for a vertical asymptote, but you're going to draw a horizontal hatched line. So you're going to have a horizontal line, you're going to hatch it like this to say this. There's not a line here, there's an asymptote here at y equals a, and a is going to be where that discontinuity occurs. So let's get into the practice problem. So we're going to be graphing asymptotes. So we're going to sketch a graph that not only has a hole, but it's also going to have a vertical asymptote and a horizontal asymptote. So it's going to incorporate all the skills we learned about. And then the equation of the graph is x plus 1 divided by x squared plus 3x plus 2. Here's a solution already. I'm going to let those disappear. And here's a solution already pre-written for you. I know it's quite a bit of work, and I'm going to go through it again with you. Again, this work, I don't think it's necessary depending on your teacher's requirements, but I do all my work and show all my work just so I know exactly what I'm doing. All right, so let me pull up a graph, and let's actually get into graphing this. So again, the equation of this rational function is y equals x plus 1 divided by x squared plus 3x plus 2. Our first rule, we're going to set the denominator equal to 0 to find the zeros. So x squared plus 3x plus 2 is equal to 0. This is a quadratic trinomial, so we're going to factor it to x plus 1 using the guess and check method. X plus 1 times x plus 2. We're going to set that equal to 0, and we're going to find the discontinuities or zeros. So we're going to set x plus 1 equal to 0. If we subtract 1 from both sides, we get x equals negative 1. Same thing with x plus 2. Let's set it equal to 0. If we subtract 2 from both sides, we get x is equal to negative 2. But right now we know that these are 2 points of discontinuity, but we don't know what kind of discontinuity they are. We need to determine, are they holes? Are they vertical asymptotes? How are we going to determine that? Well, we're going to do our second step where we're going to reduce the function. So I'm going to rewrite the function here, x plus 1 over x squared plus 3x plus 2. We're going to factor the bottom, which we already factored before. So I'm going to write this as x plus 1 over x plus 1 times x plus 2. And as you can see, there's a common factor of x plus 1 between the numerator and denominator, so I'm going to cross those off. And our reduced function, we're only going to have this x plus 2 left, and now that we canceled these common factors out, there's just a 1 left in the numerator. We're going to have x1 over x plus 2. So our reduced function is, let me write this as y because we've been going with y so far. So y is equal to 1 over x plus 2. That means that if this is our function here, we're going to have a vertical asymptote at x plus 2 equals 0. If we set that equal to 0, then we're going to have a vertical asymptote at x equals negative 2. So if this negative 2 that we found up here is going to be the vertical asymptote, and there was a common factor of x plus 1, that means this x equals negative 1 is going to be where the hole occurs. So how do we find where the hole occurs? We're going to go to our next step. We're going to plug negative 1 into this reduced function. So f of negative 1, well, that's just going to be finding the y coordinate. So y is equal to 1, 1 over, we plug negative 1 in for x, so negative 1 plus 2 is equal to 1 over negative 1 plus 2 is 1. So we're going to end up getting is equal to 1. So our hole is going to be the point. Negative 1, 1. All right, so now we found those two discontinuities, but do we have a horizontal asymptote discontinuity? So we have to determine that. So how will we determine that? Well, let's compare the degrees of the numerator and denominator of our original function. So we're going to look at the degrees. The degree of the numerator, which is x plus 1, so we're going to look at x to determine a. So that's a linear term, so that's going to be equal to 1. How about the denominator? That's x squared is our leading term. That's going to be equal to b, and that's a quadratic, so its degree is 2. In this case, a has a smaller degree than b, so we're going to have a horizontal asymptote. Horizontal asymptote at y equals 0. So that's all the work and planning we did to determine where just the discontinuities are. Now, to actually graph this, we're going to have to come up with a little xy table. And what I'm going to do, we already know there's a horizontal asymptote at y equals 0. So I'm already just going to put a hat, and y equals 0 is the x-axis. So I'm just going to put a hatched line right here. I don't need to put this in my xy table. There's no need. What I'm going to do is I'm going to put my vertical asymptote and my hole in the middle of my xy table. So my vertical asymptote occurs at negative 2, and my hole occurs at negative 1. So I'm going to put negative 2 here and then negative 1 underneath it. We know that the point of the hole is negative 1, 1. So I'm going to put 1 in my y coordinates, and we know at negative 2 it's undefined. So I'm just going to write undefined. It has no value because that will make the denominator 0, so that's undefined. Then above x, I'm going to pick 3. Above less than negative 2, I'm going to pick 3 values. So negative 3, negative 4. Oops, I'm sorry, this is hard to see. And negative 5, and then negative 1 underneath. And then I'm going to pick 3 values greater than negative 1. So I'm going to pick 2. Am I doing 2? Let me think about this. I'll do 2 values greater than negative 1. So 0 and 1. So then what I'm going to do is I'm going to plug each of these in to our reduced function, which is y equals 1 over x plus 2. So if I plug 0 in, let's just start with 0, I would get 1 over 0 plus 2, which is just 1/2. If I plug 1 in, I would get 1 over 1 plus 2, which is 1/3. And let's do the same thing up here. Negative 3 plus 2 is just equal to negative 1, so 1 divided by negative 1 is just going to be negative 1. 1 over negative 4 plus 2, well, that's 1 over negative 2, so that's just going to be negative 1/2. there's not enough space to go with this -5, but the corresponding y coordinate is going to be 1 over -5 plus 2, which is going to be 1 over -3, which is -1/3. So let's plot these points. Before we even do that, what I want to do is I want to plot the vertical asymptote. The vertical asymptote's at -2, so I'm just going to draw another hash line at -2. And then what we're going to do is we're going to start plotting these points. The first point I would plot is going to be, I'm just going to write down here, just so we know, like our signals. This is the vertical asymptote. This is the hole. We need to make sure that we graphically represent that. We did the vertical asymptote and the horizontal asymptote, so let's graphically represent the hole. That's going to be at -1, 1, so I'm going to draw an open circle there. We also have a point at 0, 1/2, so I'm going to draw that here. 1, 1/3, so I'm going to draw that here. Whoops, sorry about that menu. 1 and 1/3 there. And then I'm going to show a point at -1, -3, -1, which is here. Then a point at -4, -1/2, which is here. And then a point at negative. All right, sorry about that. So let's continue. So we have a point at -3, -1. We also have a point at -4, -1/2. And then we have a point at -5, -1/3. Now what we're going to do is we're going to connect these points. So I'm going to connect this hole to these points here, and make sure you show that you're approaching y equals 0, but make sure you're not touching it. It's kind of hard, but make sure that you're not touching it or crossing it. Same thing with this vertical asymptote here. I'm going to show that we're approaching, the curve is approaching, but it's not quite touching. And same thing with these points, approaching y equals 0, but not touching it, and then approaching x equals -2, but not touching it. And then we're going to show the curve. So that's how you would graphically represent all those three discontinuities. And that's it. I hope you enjoyed the lesson, and if you do, please continue to watch. Also, please like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Check out our website and email us at our Gmail with any inquiries. So happy you could join me, and stay tuned for the next episode. Bye!